Today we're going to be talking about linear functions in context. Now this is all very similar to what we did yesterday. However, today we're just taking what we did yesterday and codifying it and not answering necessarily every question for every problem. Let's go ahead and look at number 5 here, because I think number 5 is probably the trickiest problem on here. If we can do that one, then we'll have no problem on any of the rest of them. A narwhal whale is born 1 meter in length and grows 1/2 meter each year for 8 years. Write a linear function to represent the situation, label the axes, and graph the function. So first things first, let's just figure out what's happening. We have a whale that's born 1 meter long. In 1 year, the whale will be 1.5 meters long because it grows 1/2 meter each year. In 2 years, it would be 2 meters long, and so on and so forth. So let's go ahead and just plot those points now that we've kind of got them. We'll label the x-axis to be time, because it generally is, and the y-axis to be the length. We get to choose what year we go measure the whale at. We don't necessarily get to choose how long the whale is. The whale does. So let's go ahead and label our points. We'll go 1, 2, 3, 4, 5, 6, 7, 8. I only went to 8 years because the function told us that it's only true up for 8 years. So let's go ahead and label it this way, 1 meter. We'll go 2 meters, 1, 2, 3 meters, 4 meters, 5 meters, 6 meters. Okay, let's plot some points. At 0 years old, or birth, the whale is 1 meter long. It's 1.5 in between there. Then it goes to 2 meters at 2 years old, 2.5 meters at 3, and so on and so forth. All right. Now let's go ahead and answer some questions about it, about this scenario. Okay. What is the y-intercept in this scenario? I got that point 1 too high. Okay. The y-intercept is 1 meter. Because at time 0, the whale is 1 meter long. We can write that as a point. Start with x, then go y. The rate of change is going to be 1/2 meters per year. That word per is key here because that implies that the meters are over the years. So let's take that and translate that to a linear function. Let's use the pattern y equals mx plus b, or slope-intercept form, because we already have the y-intercept and we already have our slope. So y, or the length, is going to be 1/2 x plus 1, or 1 year plus however many years past that, you would add on additional halves. All right, let's go ahead and talk about the domain. The domain in this case is going to be from 0 years to 8 years, because that's as long as we know that this is true for. All right, and then our range is going to be from 1 meter up to 5 meters, because that's how long the whale will be as it grows. That's as far as we know. All right. Is this function discrete or continuous? Another way of thinking about this question is asking yourself, would it make sense for this function to connect the dots? I think in this case it would make sense to connect the dots, because we could, at points in between, measure the length of the whale. And we could get like half a year and measure it and get another distance. I would say this one is continuous. You'll notice down on number 8, I said that it was discrete, because that situation is about selling coins in a jar. And you can't sell half a coin to someone. That doesn't make sense to me. So it's going to be a discrete function. Question, what would the graph look like after 8 years? I don't know. There's no way to know. But my guess is it would flatten out. because all living creatures grow for a certain period of their life, and then they stay the same size for the rest of their life. At least most mammals do that. All right, so there's number 5. That's kind of the trickiest question in all of these, but let's go ahead and look at another one as well. Let's look at number 4. The temperature at the Earth's crust is about 20 degrees Celsius near the surface, and as we go up about 30 degrees for each kilometer beneath the surface. Write a linear function to represent the situation, if this model works for a depth up to 100 kilometers. Be sure to label the axes and graph the function. All right, so here's what's happening. We're starting at the surface of the planet, and as we go down towards the core, it's going to get hotter. So the elevation decreases, the temperature is going to increase. Okay, so we start at 20 degrees near the surface. Oops, it went away. Starts at 20 degrees near the surface. So at 0 kilometers down, or at the surface, it is 20 degrees. We'll do the dots in black. As we move 1 kilometer down, the temperature increases 30 degrees. So our next point, I'm going to kind of fudge it and say that's going to be 50. It's going to be right there. Let's go ahead and do our next one. That's going to be at 80 degrees. And so on and so forth. We'll do one more this way. It's going to be like right there. And it's going to be about 110 degrees Celsius. So our y-axis in this case is temperature. And the elevation is the x. I picked elevation to be the x in this case because we can choose the elevation. We don't choose how hot the Earth is. So the elevation, or the independent variable, is the one that we have control over. We don't have control over how hot the Earth is. That's just what's happening depending on how deep we are. All right, so let's go ahead and answer these questions and see if we can graph the function. The y-intercept, notice that's in quotation marks because we're not using x and y, we're using temperature and elevation. So in this case, the temperature at the surface is 20 degrees Celsius. So we could write that as this point. The rate of change, well, as we go down 1 kilometer, the temperature increases. So it's 30 degrees Celsius per kilometer. Okay, so let's take that information and make it into a linear function. I'm going to take my linear function, just write it right here, so I just have a little bit more room. My pen is a little fatter than yours, and so I'm just trying to make sure that we can see it good. Okay, the linear function, I'd say the temperature is equal to the 20 degrees that we started with plus 30 degrees per each kilometer down. So we'll call that E for elevation. Now you'll notice that even though I've got positive numbers here, we are talking about kilometers down. So if you wanted to say that was negative numbers, I could see where that would make sense. And if you wrote it that way and graphed it that way, I think that's fine. I could follow, okay? So I'd say that is our equation for the linear function. We've got the temperature, 20 plus 30 degrees down for each going that way. The domain in this case, the domain is the x values. And we know that this is true for the surface, but it's only true for 100 kilometers down. So we go from 0 to 100. We know that's true because of this part right here. As always, let me know if you have additional questions.